Hi, today we're going to do number 235, lowest common ancestor of a binary search tree. So we're given a binary search tree and two nodes, and we want to return the node that's the parent, that's like the lowest common ancestry. And lowest common ancestry, we don't have to look into it, but we see here the example. This is 2, Q is 8, the parent they have in common is 6. But like if we look at something like 3 and 9, it'll be 6, but 3 and 5 will be 4, like that. And this one, we see here 2 and 4, so the parent will be 2, and it could be the same. The lowest common ancestry could be its own value. So the key here is that it's a binary search tree, so left values are smaller than parent, and then right values are bigger than parent. And to find this LCA, we have to find where the nodes diverge, where they separate, as in here 2, 8, they separate here. So we can keep going down. We can either go left or right or return where it is. We go left. If we look at this example, go left if here 2 and 4 here, if both values are smaller than parent. Since here 2, 4, it's both small, so we go down here. But here only one value is smaller, so we return. That's what we return. And then we go right for the inverse if both values are bigger than parent. So there's two ways we can go about doing this, and one of it is recursively. And here, the times complexity will be O of H, where H is the height of the tree. So we can just take advantage of the binary search tree. H, as in if it's a balanced tree, it's going to be log n. Whereas if it's a skewed tree where it's just like a linked list, it's going to be O of n. And a space complexity since we're creating a call stack for however long the tree is also going to be O of H. And then we can solve this iteratively. And by doing that way, the time complexity was still going to be the same, O of H. However, there's going to be a constant space complexity because we can just replace the root as we iterate through. And since this has a better space complexity, we can go with the iterative way. But I'll show you both. So we're going to use this root as the tracker. So while we have a value of root here, we want to go left. So if p.val is less than root.val and q.val is less than root.val, we update the root to be root.left. And then we can just do the opposite for the right side. Else if p.val is greater than root.val and q.val is greater than root.val, root equals root dot right, and then if it doesn't hit these else, it means we found it, so we just return root. Great, and let's solve it with the iterative way. So with the recursive way. So if root is null, return null, not having it, and then we can check the conditions. If p.val is less than root.val and q.val is less than root.val, we return lowest common ancestor with root going to the left. Same p, same q. And then if p.val is greater than root.val and q.val is greater than root.val, we go to the right side. And then if it doesn't hit these, it means we have the values, and we just return the root. Great, so those are two ways we can solve this. Either we can do it recursively, where we call the function again if it's both of the values are small, we just return it back, or we can use a while loop and just update the root variable. If both of them are smaller, go left. If both of them are bigger, go right. And that's all. Thank you so much.